So hello everyone, welcome to this new seminar from the Instituto de Astrofisica Andalucía. Our speaker today is Dr. Jorge Sánchez Almeida, and he will be properly introduced by Dr. Ricardo Amorim. So Ricardo.
Thank you. Good morning, everyone. I'm very happy to introduce Jorge. He's a very good friend and collaborator from the IEC. He's one of the PIs of the Estallidos collaboration, the Estallidos project. And he has been working a lot on not only in this specific topic, but also in Star Wars galaxies and many other things. So
over time, I'm old enough to have gone through many different things.
So today he will talk about a very recent MPJ letter that has been published about the connection between Ultra Faint Dwarf galaxies and the cold dark matter paradigm. So it's all yours.
Okay, so thank you. So first of all, thank you very much for this opportunity to talk about our latest work. I'm really happy of having had the opportunity of presenting it here. And then I had to apologize for the time, which is unusual for the seminars. It's my fault, but I have to take a plane, and this was the only time available. So thanks for being here. And I start talking about the talk, the actual talk. So I'm going to talk about today about the stellar distribution in ultra faint dwarf galaxies and how this distribution is telling us that we have somehow to go beyond the collisionless cold dark matter paradigm. Okay, I'm going to present a work carried out in collaboration with Nacho Trujillo from the IEC and Angel Plastin. And what I'm going to describe is in a number of papers, but the one that sort of is highlighted here, the one that presents the result of the ultra faint dwarfs, is this APJ later that appeared like 1 week ago or so. So the talk will follow this outline. First, I will motivate the interest of wondering about the nature of dark matter. In particular, I have to talk about very low mass galaxies, where the distribution of dark matter is something that contains information on the nature of dark matter itself. In particular, or whether the dark matter is collisionless, which is the standard assumption, or is not collisionless. So remember that in the standard lambda CDM, dark matter are particles which interact with themselves and with the rest of the universe, with the baryons, through gravity alone. Okay, there is nothing else. But there are, there's a regime, very low mass galaxies, where the distribution of dark matter is telling us about whether these collisions between dark matter are as assumed in the standard model or are not. So I will motivate the interest of these galaxies and this study, and then I will explain that despite the fact that this is a kind of tricky thing to determine the distribution of dark matter in this very low mass regime, we have come across a method which is based on something, a classical Eddington inversion method that can be used to constrain the distribution of dark matter just from photometry, not from dynamical measurements. And in particular, this technique tells us that, I will argue how this can be proven, that if you have a stellar distribution, you have a galaxy with a stellar distribution with a core, so doesn't have a concentration of star in a particular place, like a central plateau in where you think is the center of the galaxy. This is inconsistent with the type of dark matter distribution that collisionless cold dark matter predict for these galaxies. Okay? Then I will explain the application of the technique to ultra faint dwarf galaxies, which do show this core-like structure in the distribution of stars, and which, because of the very low mass of these ultra faint dwarfs, tells that we don't have to go beyond the collisionless cold dark matter. And I will explain very briefly how can you use this constraint to say something about specific models of dark matter, physical models of what dark matter is. So about the motivation, I start from the very big picture. So if you look for what are the biggest questions still open in science in general, this is something, it's a report in Nature a few years ago. You find things like we don't know what is space-time, we don't know what is consciousness, we don't know how life begins, and we don't know what is dark matter. So it's one of the really, the nature of dark matter is one of the key questions in science, okay? And something which is often forgotten, I mean, all we know, but at the same time, I don't think we are self-aware really of the implications of this thing, is that this big problem of science is a purely astrophysical problem. So the only evidence we have for the existence of dark matter, which forms all the matter, 85% of the universe, comes from astrophysics. So despite the fact that there are really tens of thousands of particle physicists like looking for particles or other explanations for what dark matter is, it's very likely that the answer is in astrophysics, okay? So it's a purely astrophysical problem, and probably the solution of what the matter is will come from astrophysical evidence. And so I will start with the specific motivation of the talk. So again, this is part of the common wisdom. So if you start a cosmological numerical simulation of pure dark matter, collisionless dark matter, where the dark matter particles just interact through gravity, and you let the simulation evolve with time, you end up with clumps of dark matter. You know, well, the idea is that the galaxies are within those clumps of dark matter, and this dark matter has a particular distribution with a cusp in the center. So it tends to be concentrated in the central parts. It's the Navarro-Fein and White profile, or the Inasto profile, or something like that. So it's a very specific profile. Now, when you go to real galaxies and try to determine the distribution of dark matter, you seldom, if ever, find those profiles. This is an example. So this is the density and how it varies in a galaxy. This, by the way, again, this is something I think well known, but the standard way to determine the distribution of dark matter is through kinematical measurements. For instance, interpreting the rotation curves of the galaxy. Now, the dark matter distribution that you obtain, that's the kind of standard thing, has an inner plateau. It's density versus radial position. You get an inner plateau rather than the distribution of dark matter that you expect from pure collisionless cold dark matter simulation, from the Navarro-Fein and White profile. Now, this difference is very well understood within the standard lambda CDM as the effect of the stellar feedback. We know that in the center of the galaxies, there are enough baryons for baryonic processes to modify the overall potential, in particular, changing the whole distribution of matter in the inner parts, including the distribution of dark matter. Okay, so it's stellar feedback that transform what would be something with a cusp into something with a core. Now, exactly the same numerical simulations tells that when you remember that the idea is that you change the shape of the profile, you distribute the dark matter, providing energy to the distribution of dark matter particles, and you extract this energy from the star formation. Now, if you go to very low stellar masses, there is a moment where where you don't have enough energy in the star formation to make the transformation from cusp to cosp. And for very, very low mass galaxies, you expect that the dark matter distribution, even if you take into account this stellar feedback, is the typical collisionless cold dark matter, so the Inasto, or the Navarro-Fein and White profile, or something like that. So there is a limit of mass of the order 10 to the 6 solar masses or so. If you have galaxies with stellar masses below that, so it's a tiny little thing, then you should expect that if the dark matter is collisionless, you should expect that the potential, that the gravity that is holding those 10 to the 4, 10 to the 6 solar masses is in a Navarro-Fein and White dark matter distribution. Now, in principle, it's super simple. So if you want to know whether the dark matter collides or not, the only thing that you have to do is to go to these tiny little galaxies and measure the distribution of dark matter. So if it shows the cusp, then collisionless is fine. But if it doesn't, then you have to go beyond that thing. Now, the problem is that determining the distribution of dark matter in these tiny little galaxies is non-trivial. It goes through kinematical measurements. You have little stars, they are very faint sources, you need enough statistics, so in practice it's unknowable. You cannot do kind of a classical approach to the distribution of dark matter, the classical measurements to compute the distribution of dark matter. But something that we know is that if you go to these very low mass galaxies, 10 to the 6 or below, all of them show a distribution of stars which don't show any obvious center, okay? It doesn't have a kind of cusp in the distribution of stars. This is a radial cut of formats. Now, can you use that information to somehow constrain the distribution of dark matter in these stars? Because photometry is something doable. So spectroscopy, so dynamical measurement is a tricky thing. You cannot do it. Photometry, you can. Can you use photometry? And the answer is yes. And I'm going to tell how we approach the problem. And we approach the problem using something that is called Eddington inversion method, that basically tells you what is the distribution function in the phase space, so in velocity and position, that is needed for an observed distribution of stars to live in a particular potential, okay? You assume a potential, you measure the distribution of stars, and it tells you what is the distribution function in the phase space that you need for these two things to be put together. Now, the distribution function is a probability. So if your observed distribution and your assumed potential require a distribution function which is negative somewhere in the phase space, you know that the two things are inconsistent. And you know that this distribution of star cannot live in this potential. Okay. This is a general statement, but it works for a specific case which is relevant for the problem. In particular, it tells that if you have a distribution of a star, like the red line here, with a core, a central plateau, living in a dark matter halo with a cusp, like this one, then you need a distribution function which is negative. So stellar cores, like the ones that are observed, cannot live in cold dark matter potential. Okay. This requires some assumptions, but really you can relax them quite substantially. So the simplest is a mathematical theory. So the simplest one refers to spherical symmetry, isotropic velocities, and a couple of extra assumptions. But those can be relaxed to theorems which apply in a much broader condition. So, for instance, you don't need to have a perfect core, you don't need to have a perfect Navarro-Fringaway profile, and still quasi-cores are incompatible with quasi-Navarro-Fringaway profile. So, if you're familiar with this Navarro-Fringaway profile, it has a problem in the center, it diverges in the center. But there are other profiles that also describe the distribution of collisions called dark matter, like the Nassau profile, that don't have that singularity, and still the inconsistency between stellar cores and the potentials remain. It also holds for non-spherical systems. So for axisymmetric systems, still you'll find the inconsistency, and even you can relax the requirement of isotropic velocity distribution because you have something that is called obstacle merit, where the distribution of velocities is like isotropic in the center and radial in the outskirts, which is precisely what you expect from numerical simulations or what is going to happen with these galaxies. Then still the problem remains. So stellar cores inconsistent with Navarro-Fringaway with potentials coming from collisionless cold dark matter. Now, application to a specific case, and this is what is in the letter. So we found 6 ultra faint dwarf galaxies. By the way, for you to have an idea of what I'm talking about, are these color points. So it's something really, really tiny. Okay, I'm talking about satellites of the Milky Way with typical stellar masses of the order of 10 to the 3, 10 to the 4 solar masses. Okay, we know, well, it's a galaxy because are fully dominated by dark matter. The kinematical measurements that you can do here tells you that the velocity dispersion is so large that typical dark matter masses are 1,000 times the stellar mass. So the issue is that if you compute what is the surface brightness distribution of these ultra faint dwarf galaxies, surface brightness versus radial position. So all ultra faint dwarfs show the same profile, and all of them show a core here. But remember that has a problem for living in a collisionless colder matter or Navarro-Finland white profile. I have no time to go into the details, but basically what we have done is to use this equation that tells what is the density in stars that you have given a distribution function weighted with something that depends on the potential. So this, you assume a potential, you can compute this function, and you make some sort of linear expansion of the observed density and determine the distribution function. That's overall the way to go. And these are the results, okay? So we try to reproduce the observed distribution of stars, which are these dots here, assuming potentials that are derived from core Navarro-Finland white type mass distributions, like this solid point here, or core potentials, like this dashed line here, these two, the blue and the other one. Now, if you assume potentials that are collisionless cold dark matter, then the distribution function in the phase space is this red line here that requires to be negative. So this thing is not living in a Navarro-Finland white potential. If you assume that the potential has a core similar to the one that the stars have, then you have no core. The distribution function is positive error. So you can really discard that these ultra-faint dwarfs are living in a colder matter potential, the potential created by collisionless colder matter. Now, the technique that we are assuming makes a number of assumptions. I talk about spherical symmetry, isotropic velocity distribution, and so on and so forth. You can analyze all the possibilities in detail to come up with the idea that this is not an issue, so that still none of these things explains why these tiny little galaxies are living in a potential that is not collisionless colder matter. Okay? For instance, the isotropic velocities I mentioned, then you can relax this assumption and still something which is realistic, like these optical memory models, show the cores to be inconsistent with collisionless colder matter potential. The spherical symmetry, you can relax this assumption and still have an inconsistency. This I hadn't mentioned, but I'm going to mention it here. These are satellites of the Milky Way. So they are suffering tidal forces of the Milky Way. You can think that these tidal forces might modify the distribution of dark matter, but we don't think that that's a good explanation for the presence of cores, and so for the presence of a core dark matter distribution. For two reasons. The first one is that these tidal forces are expected to be different from different galaxies. And remember that the distribution of stars of all the galaxies, of all the 6 ultra-faint dwarfs, is the same. So this is not the kind of thing that you expect to happen from tidal forces. Some will be one way, some others will be a different way. This is one of the arguments. The other one is that truly tidal forces disrupt satellites, but they start like crabbing outward in. So they move the outer part first, and then the last part that is preserved, so to say, is the concentration of dark matter. So the numerical simulations of collisionless cold dark matter tell that even in tidal dwarfs, the inner parts are Navarro-Finland white. So tidal force doesn't seem to be the explanation. Again, I say that we are assuming Navarro-Finland white potential, but this is not a big restriction. It also holds for other potentials. I'm talking, okay, this Eddington inversion technique tells you what is the distribution of that, or the distribution of mass that provides the potential where your galaxies are living in. So it includes the distribution of dark matter plus the distribution of stars. So in principle, you have to take into account the distribution of stars. But remember that these galaxies have dark matter mass that is fully dominating the whole potential. So the fact that you include or not the distribution of the star doesn't change anything. So this is not an explanation, and I'm not going to enter into the technical subtleties of computing the distribution of stars. So, and this is kind of the take-home message. So the stellar distribution in ultra faint dwarf galaxies is incompatible with the collisionless cold dark matter paradigm, because they live in a core potential that shouldn't be there if the collisionless cold dark matter paradigm holds. So somehow it's telling that we have to go beyond collisionless cold dark matter, which are very good news. So the idea, I want to make this thing clear, is not that you have to, let's say, change the paradigm that we have for cosmology. This is a kind of small modification in the whole picture. What it's telling us is that we finally have an argument to go beyond collisionless cold dark matter, which, by the way, is a purely phenomenological model. So we don't have a physical model for collisionless cold dark matter. All the models that people have been building over time, and I'm moving into the next issue, all the models, all the physical models require some sort of interaction between the dark matter particles and the baryons. Okay, if you want to construct a physical model, there should be an interaction. There should be some kind of interaction between the dark matter particles, low enough to be consistent with almost collisionless cold dark matter. But we have found kind of a hint of a deviations from this idea, and this starting point to try to constrain or to test the different ideas that we have about what dark matter could be. I don't have the time nor the knowledge to summarize all the different models that we have, physical models that we have for dark matter. There are tens of them, so it's a kind of complicated thing. But what I'm going to do here is to try to illustrate how this idea that you have collisions between dark matter particles can be used to constrain specific models. So this had to be done in a case-by-case study. So we have to pick up a particular model for physical model for dark matter and see how the fact that in this dwarf galaxy you find collisions, how this, what are the constraints, are the implications of these things into the physical models. I'm gonna use to illustrate how this works, talking about something that is called in the jargon self-interacting dark matter. Basically, again, next step, simple, that the dark matter particles, in addition to the gravitational forces that they suffer, they also interact with themselves through other forces that are not suffered by the body. So the dark matter particles are colliding, and this explains, for instance, the existence of core. And I'm going to describe this self-interacting, the constraints imposed in this self-interacting dark matter model. So the first thing that is important to keep in mind is that this dark matter halo, collisionless cold dark matter halo, they are imposed. So Navarro-Flynn and White profiles, they come from the initial conditions provided by cosmology. So the dark matter particles don't collide with themselves. And so in a way, they reproduce the initial conditions evolved thanks to the effect of gravity over time. So they are like replicating initial conditions. Okay. Now, if you let the dark matter particles to collide, all of a sudden they lose memory of this initial condition. And you might retain a distribution consistent with a system that is self-gravitating, but is in some sort of thermodynamic equilibrium. And in this case, this was proven in the thesis of Ángel Plastino long ago, that if you have a system which is in thermodynamic, self-gravitating system in thermodynamic equilibrium, which collisions cold dark matter cannot reach over Hubble time, then if you have a system that collides, then it reaches a distribution, is a polytropic shape with an inner core. So you automatically have cores if you allow the dark matter particles to collide with cross sections which are large enough. Okay. Now, that's the tricky part. The tricky part is that cross sections should be large enough so that the particles collide to reach thermodynamic equilibrium within a Hubble time. Okay. Now, there's another technical issue here that I'm not sure that so if this self-interacting dark matter produces the cores, you need enough collisions for the system to be in thermodynamic equilibrium. But if you have too many collisions, there's something weird happening with the halos of self-interacting dark matter particles. So the collisions are so efficient that they tend to kind of kick away the high energetic particles that are in the center of the potential, and this creates an increase of the central density. And this is a runaway process that in the end, again, reproduce a halo, which is not exactly an Unraveling wire halo, but increases the inner density to a point that again is inconsistent with the observation. So the point is that if you start with a halo with this collisionless dark matter, you allow collisions to operate, and this produces a core. Well, the pointer is not working. See what it is. So you start with a halo, which is the kind of collision is called dark matter halo. Collisions produce a core, and you need enough collisions so that this core is created during the Hubble time. But if you let the system evolve in time, or you increase the cross section, in a given moment you have the core collapse. So you have this core that over time is increasing. So in the end, what I was about to say is that in this scenario, self-interacting dark matter, and the collisions are elastic, then this sets a limit for the cross-section that characterize the process between 10 and 72 in these funny units that I use in astronomy. Okay, now in this model, it has to be consistent with the other constraints that we have, telling that the dark matter does not collide. In particular, the constraint provided by the Ballet cluster that I'm sure that you all have heard about. Not this constraint, but the fact that the Ballet cluster is probably one of the more clear observational hints that we have for the existence of dark matter. Remember, this is a cluster of galaxies which is colliding. The colliding occurred some time ago, and the stars and the dark matter has passed by, so that in the center of the collision, the center of mass, the gas that was associated with the two subclusters interact through hydroforces, so they are in the center of mass, whereas the dark matter and the stars have passed by, and they are separated from the distribution of gas. This is the Ballet cluster. So the distribution of gas is offset compared with the distribution of dark matter. Now, I'm saying that the dark matter collides. So in a sense, it starts to be behaving as if it were baryons. So if the collisions are important enough, what should happen is that you have dark matter coinciding also with the distribution of gas. Okay, dark matter collides, and so if it collides, it's gonna somehow behave as baryons, suffering some sort of forces. But you don't observe this thing. Okay, you observe that the distribution of dark matter coincides with the distribution of stars. The stars are purely collisionless. Now, this is again well understood within the theory, because it might sound a little bit counterintuitive, but it is not. Because in this self-interaction dark matter, you expect the cross-section to be strongly dependent on the relative velocity of the dark matter particles. It's exactly the same as happened, for instance, with gravity. So if you have two objects that are interacting through gravity, if the relative velocity is very large, the time scale of the interaction is extremely short, and almost nothing happens. Okay? Whereas if you have a relative velocity between the two objects that are interacting through gravity, which is low, the relative velocity needs a lot of time for the two objects to do whatever they want to do, and so the interaction is very, very strong. So you expect a very strong dependence of the cross-section on the velocity. And actually, the velocities in clusters are thousands of kilometers per second. The typical velocities in the tiny little galaxies I was describing is a few kilometers per second, maybe 10 kilometers per second. So you expect that in the scale of clusters of galaxies, you don't see the effect of the cell interaction, but it's stronger when you are dealing with tiny little galaxies.
Excuse me, we can measure the dark matter profile
through lensing, through gravitational lensing.
So you're really measuring the gravitational potential, not the dark matter profile, right?
Yeah. Yeah. But you know, most of the gravitational potential is set by dark matter. In any case, I don't know exactly how this was done. So whether you have the distribution of mass in stars, you have the distribution of gas. So in principle, you can decontaminate if that were an issue. The potential, so the dark matter from the rest. You know the distribution of gas, you know the distribution of stars, you measure the overall potential, and so you can, in principle, subtract the two things if that thing is an issue, but I don't think it is. Okay, because it's, I mean, the amount of dark matter is much, much larger than the mass that you have in gas or stars. Okay. Any other question or, I mean, in the very last view. So this is the take-home message. So the very short version is like in the Lambda CDM. I think we have found hints that we have to drop this C that stands for collisionless core. Okay, so we have a hints. I would say that is more than hints that that dark matter interacts beyond gravitational forces. The long summary is this other one. So I mentioned that we know that stellar feedback that in principle is able to modify the overall potential and turn the cusp dark matter halo predicted by collision cold dark matter into a core. Stops working when you reach a stellar mass in your galaxy below 10 to the 6, 10 to the 5 solar masses or so. So in principle, if you find cores in halos of galaxies below this stellar mass, then you know that you have to go beyond collisionless cold dark matter. Now, the tricky part is that you don't know how to measure the distribution of dark matter in these tiny little objects. But I pointed out that we have developed a technique based on the Eddington inversion technique that tells you that, yes, you can use photometry to say something, at least constrain the distribution of dark matter. And in particular, this technique tells that you cannot have a core in the stellar distribution living in a collisionless cold dark matter halo that has a cusp. Okay. We have applied the technique to a number of ultra faint dwarf galaxies that show core-seed stars. And so they are living in potentials that are not the potential that you expect from collisionless cold dark matter. And so it is telling us that the dark matter particles are doing something else in addition to interact through gravity. So that somehow they had to create these cores out of the physics that they are undergoing. And I say that the implications for specific physical models for dark matter are complicated. One had to study every case individually. And I illustrate how this might work for self-interacting dark matter. And that was it. So thank you very much. And I'm ready to take questions if you.
Okay, so time for questions. So thanks a lot for the talk. I wanted to ask why you see this effect of the self-interaction of dark matter only in small galaxies? Like, why is it so relevant that there is a small stellar mass, or why don't you see this in our galaxies?
So you're referring now to the self-interacting dark matter model.
Yeah, so you do an analysis, this inversion method, to reach the conclusion that you cannot fit the profile.
And this is general. It doesn't have to do with the mass of the galaxy.
Okay.
So if you find a core, which is a common thing, so you know that they are living in a potential which is not a Navrov away potential. The point is that when the mass is large enough, then stellar feedback can do the work, can change the Navrov away potential into a core potential. But there is a limit of mass below which, stellar feedback cannot do the work. And these galaxies are already in that regime. So the stellar feedback cannot modify the distribution of dark matter. If you go below, above 10 to the 6 solar masses, then stellar feedback modifies the distribution of all particles there, including the dark matter particles, and create a core. In a way, to normalize the distribution of dark matter particles. The tricky thing here that we managed to measure the distribution of dark matter in galaxies below this mass limit, where stellar feedback is unable to do the work.
So above that limit, there is no hope to distinguish whether dark matter is self-interacting. For galaxies that are of this limit, you cannot disentangle stellar feedback from
it's a tricky thing, okay? But now that we have an idea that this is working, then the issue is to try to disentangle the effect of stellar feedback from something else. And I'm sure this is one of the things that I have in mind to do in the near future. So it's a non-trivial thing, but all this issue about the nature of dark matter is very, very complicated. It's a fishy thing that, we progress everywhere. But in that case, what you would have to do is to see how to separate the two effects, okay?
And the cross-section that you find for the self-interactions of the dark matter, because I guess you can put some constraints on how much can self-interact. When you plug it in the cosmological evolution and try to see things like Planck data or accelerated expansions through supernova, does it have an effect?
No, very little, very, very little.
But Planck is very precise, right, with the multiple structure.
Yeah, but this is something that, remember, that is particularly important when you have high velocities. And no, it has really no impact on cosmology. On scales that are larger than the kiloparsecs is absolutely irrelevant. Yeah.
I would have expected an impact on the S8 tension, this mismatch that is apparently on how much it tends to cluster matter, but maybe I'm misguided.
I think that it depends on the scales. All the scales that you have in mind, the ones that are sampled by Planck, are much larger, far larger than the ones that we are talking about. These are, in the L expansion that is used in Planck, is something that is not reached.
Okay, thank you.
Thank you for the talk. Well, I have a comment maybe you want to develop, but the feedback is quite dependent on the fraction of massive star that you have in the galaxy. So how much all the calculation depends on the assumption of the element?
So it's excellent. I mean, I'm happy that you made the question. So it's true that the effect of the stellar feedback is extremely model dependent. So depending on how you implement the stellar feedback, you get things which are different or not. Now, the question is that in this case, this doesn't happen because it's an order of magnitude thing. So you don't have enough energy. It doesn't matter how you do the feedback. You don't have enough energy in the stars to modify the potential. Okay, so all the models, all the feedbacks that you can think of, or the simulations that are around, and even the analytical estimates tells you that, yes, I mean, it might be 10 to the 6 or maybe 10 to the 5, but below that thing, you don't have energy. And so feedback, the way you implement the feedback is secondary. You don't have energy to do the change.
I have a question that's probably unrelated, but I've noticed that you focus the analysis on the inner parts of the galaxies currently, just looking at the stellar component. So I'm wondering whether if you go in the outer regions, let's say tracing the gas out to, I don't know what radius, would you see a kind of change in the distribution? Or do you think it's not relevant?
No, what happened, it is relevant. It's the whole distribution of dark matter that is relevant. But the issue is that the densities are larger in the central parts. So all this thermalization is going to happen sooner in the inner parts than in the outer parts. So what I would expect, and I think this is something closer to what happened, is that the inner parts are thermalized and the outer parts are Navarro-Fein distribution. But this is something to be studied in detail in the near future, I would say. So yes, this is relevant. This is happening everywhere. The densities are much lower in the outer parts. So all the process of thermalization will be slowed down in the outer parts. And so it will be closer to a purely collisionless called dark matter halo. Whereas in the inner parts, I mean, depending on the model, because the densities are larger, you reach the thermalization sooner. Okay, but this is work to be done. So it's
Hi, Ms. Doc. This may be a bit of an ignorant question, but every simulation that I've seen assumed a cold dark matter model. So I was wondering if there is any other big simulation that assume another kind of dark matter that is compatible with the core distribution that you're assuming or proposing, that also leads to other observational stuff like the large scale structure.
Yeah, I try to, okay, so most of the simulations are collisions called dark matter, but people is taking seriously alternatives. So there are cosmological simulations for things like fuzzy dark matter, or it's fairly developed, the simulations for self-interacting dark matter. So people have implemented this possibility that you have collisions, and even inelastic collisions, things like you have kind of excited atoms of dark matter that absorb some sort of dark photon emit. I mean, there are simulations about that thing. Now, these simulations, again, one of the things that you learn from them is that you need low cross sections when the structures are massive, like in clusters. And when you go to very low masses, then create the cores, you need collisions with a cross section similar to the one that I was mentioning here. So there are not many simulations. So let me try to answer your question. So there are not many alternative simulations, but there are some of them. Okay, even the main groups are already put in, because it's a kind of easy. I mean, it's not completely trivial, but I understand that it's among the simplest things that you can implement in a cosmological simulation is the self-interaction of the dark matter. And there are a number of simulations that already take that thing into account, and they produce the cores depending on the cross-section. And for clusters, to prevent this core collapse that I mentioned, the cross-sections can be very large. In dwarf galaxies, the cross-sections have to be around 2 or so to create the cores in the time scale of the Hubble time. So it's consistent with what I have already mentioned.
No questions? Yes, Jorge.
And maybe this is a naive question, but I was wondering, this whole scenario with the cores that happen with really low stellar masses, as we move to higher redshift, we expect these objects to be more and more common, can help also in the evolution or co-evolution of AGMs and host galaxies, like increasing the statistical number that we may find in higher redshifts, or that's nothing to do?
I have no idea how to answer this
And I
question.
guess
No, I don't think that it's going to be very important, because to thermalize, basically, you need to create a core. And a core is the solution of self-gravitating system that is in kind of thermodynamic equilibrium. And you need something, and you need time to reach the thermodynamic equilibrium. And this something is the same, no matter, because it's something that depends on the physics, but the time is also an issue. So as you go to the early universe, this is going to be less and less important. So again, I think I mentioned at the beginning, so the issue is not so much changing the cosmological model. The issue is to try to find a gateway to say something about the nature of dark matter, okay? That start to show deviations so start to show physical properties that can be tested against physical models.
the question was, observationally, we still see gas profiles sometimes, right?
Very, very seldom. So you might have an example, and then when you double check, it's not clear. So I'm not aware of any, basically. By the way, you can create this. I mean, this runaway process is happening in larger galaxies. So you may create tiny little cores that if you don't have enough spatial resolution, you identify like something that's growing to the inner parts, but it's not, okay? But there are claims in the literature of this galaxy has an abruptly white halo. But there are specific cases of this and that, and I mean, very uncertain, I would say.
It would be an issue of spatial resolution.
In massive galaxies, more massive galaxies, yes, I think.
Okay, any more questions here, or maybe in Zoom? No? Okay, so let's thank Speaker Jorge again.